Hello everyone. Today we will discuss about quantum well lasers. In the previous class, we have discussed about double heterojunction lasers. We know that when you reduce the size of nanostructures, that is especially in quantum wells and dots, the energy levels will become discrete. Here also, when the active layer thickness of DH lasers is reduced to the order of the de Broglie wavelength, the active region means the gallium arsenide, the narrow band gap semiconductor material. So there will be condensation of energy levels. So such devices are called quantum well lasers, and the structure of the quantum well laser is shown here. Basically, a quantum well laser, it is a heterojunction laser with quantum well for electron hole transition. So the active region will be, still it is gallium arsenide. So the main point of this laser is the sharp energy levels, that is a discrete energy levels, that is quantized energy levels. In the bulk materials, the energy levels will be continuous. It is very sensible to the temperature. Here the energy levels will become discrete because the thickness of the active region, thickness of the well, is minimized to the 2D levels. So because of the difference in band gaps and the change in due to the change in refractive index, the structure provides the optical confinement and the carrier confinement. Now we can check the energy levels of electrons and holes in the quantum well. So a single quantum well structure is a double hetero structure. There will be double heterojunctions between L gas and gas in the left side, and on the right side also there will be another heterojunction, L gas and gas. So the active region is a gallium arsenide. So the quantum well for an L gas heterostructure is shown here. Here the quantum well thickness, that active region thickness, is around 10 nanometer. So when you reduce the thickness of the quantum well, the energy levels will become discrete. So here there are two discrete energy levels, E1 and E2 at the conduction band. And at the valence band, there are again two energy levels, stable energy levels, EH1 and EH2. So another point is that when you further reduce the thickness of the quantum well, the energy levels, the number of discrete energy levels get reduced. Okay, that's an important point. So when you decrease the thickness of the active region, actually you are going to change the effective band gap of the material, effective band gap of this quantum well structure. Then consider there are two discrete energy levels as shown in this figure, in the conduction band and valence band. So there can be transition of electrons and holes between these allowed energy levels, so that there will be emission of photons and the amplification, that is the lasing actions, just like the DH lasers. Then here the effective band gap. So what is the actual band gap? The actual band gap of this quantum well is expressed as shown as EG here, E suffix G here. So what is the effective band gap? Here the effective band gap of the quantum well for n is equal to 1, that is a EG, that is band gap of gallium arsenide, plus E1. E1 is the stable quantized energy level in the conduction band, plus EH1. EH1 is the stable quantized energy level in the valence band. So the effective band gap is the Eg plus E1 plus EH1. That means the electrons can only withstand in the discrete energy levels. So based on this effective band gap, the wavelength of the photons are also get changed. So how will you change the wavelength of the laser? By simply reducing the size of this quantum well. When you reduce the thickness of this quantum well, the effective band gap are also get changed, so that you can easily change the wavelength of photons. Here the energy states are discrete. Since the laser transition occur between two well-defined energy states, the wavelength of laser emission is sharp, it is constant, so that the laser will be highly monochromatic. If you consider a normal PN junction lasers, semiconductor lasers, the energy states are continuous in the conduction band and valence band. So consider the conduction band energy levels, it is continuous. So they are sensible to the external temperature because it can absorb the external energy, and the electrons can move from one energy state to the other energy state, to the higher energy state. So it will reflect on the characteristics of the lasers. So the wavelength of the laser will not be unique, or it will not be monochromatic for conventional lasers. They are very sensible to the temperature, external energy. But here the energy levels are not continuous. There is sufficient gap between two available energy states. If we further decrease the size of the quantum well, there will be very few number of available energy states in the conduction band. So due to this discrete energy levels, the emission of light, there is a wavelength of this light will be constant. It is highly monochromatic. Then another attractive feature is that the quantum well laser, we can reduce the quantum well thickness for a desired wavelength. That means when you reduce the thickness of active region, actually you are going to change the exact band gap of the active region. Then there is one limitation for quantum well lasers. It's a poor optical confinement, but this drawback can be reduced by using multiple quantum wells in the active region. That is MQWs, multiple quantum wells. Next, the advantages of quantum well lasers. So the first point is the low lasing current required. There is a threshold current required for the lasing action is on the lower side. Then high quantum efficiency, then high output power, then it is not sensible to the temperature, it is on the lower side, low temperature dependence, then high speed and wide range of wavelength selection. Very important point. By reducing the thickness of the active region, you can select the desired wavelength. Okay,